So now the topic of interest is wave optics. So in the wave optics, so basically the question will be asked from Young's double slit experiment, ydse. So majorly, so that is in addition to that, we are having the questions from diffraction and as well interpretation. So the most focus on ydse only. So in the wave optics, first we are thinking of interference. So interference means this is variation of intensity, variation of intensity of light, variation of intensity of light in the redistribution, redistribution of total energy of interfering waves is called as interference. So that means actually when we think of a light, when the two light waves are superposing with each other, so after when they superpose with each other, so in the superposed region, so the total intensity will be distributed. So that means instead of having uniform illumination, so we are going to have the intensity is distributed between two regions, bright and dark regions. So that means so whatever may be the light present in the this region will be added to this region. అంటే ఇక్కడ డార్క్ రీజన్ ఎందుకు వచ్చింది అంటే ఇక్కడ ఉన్నటువంటి ఇంటెన్సిటీ ఈ రీజన్ షిఫ్ట్ అయింది అని అర్థం. ఇక్కడ ఉండాల్సిన ఇంటెన్సిటీ కాస్త ఈ రీజన్ షిఫ్ట్ అయింది అని అర్థం. అంటే ఇక్కడ ఏం జరుగుతుంది, రీడిస్ట్రిబ్యూషన్ ఆఫ్ టోటల్ ఎనర్జీ జరుగుతుంది. సో ఈ ప్రాసెస్ ని మనము ఇంటర్ఫిరెన్స్ అని అంటాం. అంటే నా ఉద్దేశం ఏంటి అంటే వెన్ టూ వేవ్స్ ఆర్ సూపర్పోజ్డ్ విత్ ఈచ్ అదర్, యూనిఫామ్ ఇల్యూమినేషన్ ఉండాలి. యూనిఫామ్ ఇల్యూమినేషన్ లేకుండా మనకేంటి ఆల్టర్నేట్ బ్రైట్ అండ్ డార్క్ ఫ్రింజెస్ వస్తుంది. అంటే మీనింగ్ ఏంటి అంటే సో ది రీడిస్ట్రిబ్యూషన్ ఆఫ్ ఎనర్జీ విల్ టేక్స్ ప్లేస్. అంటే ఈ ప్లేస్ లో ఉండాల్సినటువంటి ఈ ప్లేస్ లో ఉండాల్సినటువంటి లైట్ కాస్త ఇటువైపు వస్తుంది అని అర్థం. అది మనకు నెక్స్ట్. So we are taking some examples for the devices by which we will obtain the interference. So one is Fresnel biprism and Lloyd's mirror. Fresnel biprism and Lloyd's mirror gives virtual image sources. For a point source of light. So generally for the interference we require two light sources. Generally for interference we require two light sources. But here to get the two light sources we are using Lloyd's mirror or Fresnel biprism. For example, if you take the biprism, it looks like this. So we are taking a simple source of light. So from the source of light we are going to get two light beams. So maybe this is S1 and this is S2 we will call. So these two waves undergo superposition. And we are going to study the superposition of the light. Next we are taking the required condition for interference. So that is the two sources should be coherent. The two sources must be coherent. two sources must be coherent. Coherent means the two light rays which are emitted from the source. The two light rays which are emitted from the source. Have a constant phase difference. అదొకటి కండిషన్. అండ్ ఇంకొక కండిషన్ ఏంటి అంటే the two sources should be monochromatic. So analyze this term, monochrome. Monochrome means single color. So obviously monochromatic means single wavelength. So that means white light should not be used. White light should not be used. Only like the sodium vapor lamp. So we know street lights. The old street lights we are having, they used to emit yellow color light. So those are the best example of monochromatic light sources we are taking. And one more thing is the two sources must be close together. And two sources must be narrow. So that means they are of very small size. They should be of very small size. Okay, these are the desired conditions for your interference. So actually in the interference, the most important topic is ydse. So before discussing the ydse, first we will try to understand what is a constant phase difference. So let us understand this. Suppose I am taking two sources S1 and S2. So we are discussing about the light waves which are emitted like this. So this is one wave and this is another wave. Suppose we have a similar wave from the S2 also. Suppose whenever you observe the starting points, so they are started from same position. So after some time, maybe they are at some point P I'm taking. Again, this is the point P. So at the point P, at the same point you are observing, so the wave traveled from the S1 and as well as S2. So we will see that their path covered is same. Suppose if you take the path covered by the first wave as, let us say, this is the lambda and this is the additional is lambda by 2. So the path length covered is 3 lambda by 2. And here also we will take the path length is 3 lambda by 2. So after some time, the path difference, their path difference is equivalent to 0. So x2 minus x1 we are taking. And we have a condition for the phase difference. Phase difference is equal to, generally we will write 2 pi by lambda into path difference. So that is equivalent to 0. And after some time we are taking another point, let us say Q here. At this point I am taking Q. So this is the discussion at P we are taking, and this is the discussion at Q we are taking. So at Q, when you are taking, we are searching for the path covered by the first wave. X1 is equal to, right now if we calculate, so we know that this is the lambda and this is another lambda, this is another lambda, and this is another lambda by 2. So that is 2 lambda plus lambda by 2 means 5 lambda by 2, 5 lambda by 2. And x2 is equivalent to, again it is 5 lambda by 2. So therefore the path difference is equal to 0 and phase difference is equivalent to 0. So that means anywhere you can observe, these two waves maintain a constant phase difference of 0. They maintain a constant phase difference of 0. So I'm taking another example rapidly. For example, if you take a wave like this, and we are taking another wave like this, another wave like this. So whenever you compare, at any place you can compare, they have a constant path difference of, let us say, lambda by 2, and a constant phase difference of 5 radians. 5 radians. So next, we are taking the most important ydse, Young's double slit experiment. So for the ydse, to understand any problem on the ydse, the following diagram is very important. So let us focus for a while. For example, I'm taking, this is the two parallel slits. S1 and S2 we are taking. So this is S1 and this is S2. The distance between the two light sources we are taking as small d. This is a small d. Suppose the light ray is emitted from the S1 and as well as S2 we take. So we would think the first one is having intensity I0 and the second one is also having intensity I0. So with the separation capital D from the slits, so you are taking a screen. Suppose I am taking a screen here. This is a screen. This is a screen. So we are assuming two light rays which are originating from the S1 and as well as S2. So this is one light. And this is another light. So this is the total path length covered by the first light ray, and S2P is the total path length covered by the second light ray we are taking. And now at the center, so between the two light sources. So here on the center of the screen, we are going to get central maximum. We are going to get central maximum. And you have been observing at a distance y. At a distance y. So that means all the distances on the screen are referred in the terms of y. And the distance between the slit and screen is known as capital D. So this is called as double slit. Double slit means two openings we have. That's why it is called as Young's double slit experiment. Okay. And we have been considering another reference line. Suppose I am taking a reference line which is originated from the center of light sources like this. If this is the theta, and according to the geometry, so this angle also becomes theta. This angle also becomes theta. In such a case, we will take this is the d sin theta. This is the d sin theta. Okay. First, we are understanding the path difference. The path difference between the two light waves. Between two light waves which are undergoing superposition. Which are undergoing superposition. So simply we will take the path difference as always delta x, that is S2P negation S1P. We are taking the difference. So from the diagram we will say that it is d sin theta. It is d sin theta. The path difference is equivalent to d sin theta. So here we will have the conditions for the path difference. Suppose if we take for bright fringe, or before taking the bright fringe, just we will imagine that. So tan theta from the diagram is it is y by capital D. So for small values, sin theta is approximately equivalent to tan theta. Sin theta is approximately equivalent to tan theta. So that is equivalent to y by D. So therefore, the path difference delta x can be defined as d into y by capital D. Delta x is equal to d into y by capital D. So this is most important relation ever in YDS. So we can do almost every problem by using this relation. Or you can call the delta x as x. X is the path difference, no issues. So this is the very famous equation. Almost we can do every problem from this equation. So this is path difference. This is path difference. Small d is nothing but this is the distance between two slits. Slits we are considering as sources of light. Both are same. Actually, before this we have a light source. So here we have a light source. So from the light source, the light ray is emitted like this, and the same light is passing through double slit. And capital D is nothing but it is the distance between slit and screen. Distance between slit and screen. And Y is the nothing but this is the position of observation. This is the position of observation on the screen from central maximum. So this is the discussion we have. This is very, very important. And before analyzing anything, so first we will take the required condition for path difference. So for bright fringes, what is the nature, and for dark fringes, what will be the nature. So first one I am taking for bright fringes. For bright fringes, we will take the path difference. Instead of delta x, I am simply calling it as x, no issues. Path difference x is equivalent to, we have n lambda. So path difference for bright fringe x is equivalent to n lambda. So n equivalent to 0, 1, 2. So you need to understand the beauty, because here we have central maximum. So that's why we have zeroth number. So this is the first bright fringe and this is the second bright fringe, and we know everything from that. So when the path difference is equivalent to n lambda, just now we have seen the desired equation from the ydse, that is y by d is equivalent to x by d. This is a very famous one. So the above one I am writing. Just we are taking the above equation. This equation we are taking the same equation. So y by d is equivalent to x by d. This is a very, very popular one. So next I am taking y by d is equivalent to x, means for bright fringes you are taking n lambda by small d. So therefore y equivalent to n lambda d by small d. Y equivalent to n lambda d by small d. So simply y is nothing but this is the position of nth bright fringe, the position of nth bright fringe from central maximum, from the central maximum. And if we need angular position, so let us say this is the theta. So let us see what is the angular position. Angular position means in the diagram nothing but the theta. For example, this is the theta and this distance is capital D. This is the screen. On the screen you are observing a distance y. Angular position is theta. So that is y by capital D we are taking. Y by d is equal to n lambda by small d. N lambda by small d. So this is about bright fringes condition. So but before understanding anything, so first we used to understand about the central maximum and their respective path difference and intensity condition. So first we will take about central maximum. So when we think of the central maximum, actually this is the double slit experiment. This is the S1 and this is the S2. And if this is the screen, on the screen the two light sources they used to superpose at the center of the screen. So here clearly we will see that, so as these distances are equal, equal distances, this distance and this distance are equal, so automatically S1P definitely equivalent to S2P. So in that case the path difference is equivalent to 0 and the phase difference is equivalent to 0. And here we have the final intensity I. So I'm taking I1 equivalent to I0 and I2 equivalent to I0. So we will take the intensity expression as I is equivalent to I1 plus I2 plus 2 into root of I1 I2 of phi. This is the general expression. So we know this from our principle of superposition. This is the resultant intensity. This is the resultant intensity expression. So we know that I equal to I1 plus I2 plus I1 plus I2 plus 2 into root of I1 I2 cos phi d. So I1 is nothing but I0 and I2 is nothing but I0. 2 into root of I1 I2. So here I will take I1 equal to I0, I2 equal to I0. And the phase difference, this here phi is nothing but phase difference, that is equivalent to 0. So simply we will get I equivalent to I0 plus 2 into root of I0 into I0. So that equivalent to finally we will call I central maximum, that is equivalent to 4 I0. Or in some questions it may be referred as I maximum, no issues. I central maximum that equivalent to 4 I0 here. So therefore the final intensity expression, I'm writing the intensity at any point where the phase difference between the two waves is, so when we are using two sources of same intensity, so we know the formula I equivalent to I1 plus I2 plus 2 into root of I1 I2 cos phi. So from there we are writing I1 as the I0 and I2 is the I0. plus 2 into root of I naught into I naught cos square. So by substituting everything, we are going to get I equivalent to 4 I naught into cos square of 5 by 2. So this is the expression for resultant intensity. So this is the expression for resultant intensity on the screen. I equivalent to 4 I naught into cos square 5 by 2. So we can locate any point we will find out this. Okay. So this is about central maximum and as well as Benjamin. And we will continue the discussion in some typical questions. So they used to ask the intensity. They used to ask the intensity of any fringe, which is at a distance, which is at a distance y from central maximum, So here what is my intention is, actually we know the central maximum intensity very well, but if somebody asked about the intensity of any fringe at a particular distance from the central maximum on the screen. So just now we have been thinking this is the central maximum, but my intention is we are locating a point P which is on the screen at a distance y, So I need the resultant intensity here, at this point. So అక్కడ మనకు కావాలి. సో దాన్ని ఎలా చేస్తాం అనేది ఇంపార్టెంట్ చాలా. So generally, I'm taking the general expression for the coherent waves, I equivalent to 4 I naught into cos square of 5 by 2. This is known to us. And instead of 4 I naught, we are taking I maximum into, instead of 5 by 2, first we will understand the relation phi is equivalent to 2 pi by lambda into x. Phase difference is equal to 2 pi by lambda into path difference. So therefore pi by 2 is equivalent to, I'm taking pi by lambda into x. But in any ydse problem, just now as I promised, we will use this equation y by capital D is equal to x by small d. X is equivalent to, instead of x we will get y small d by capital D. So therefore pi by d is equivalent to pi by lambda into x means y into small d by capital D. So that equivalent to pi into y by, so we will get lambda d by small d. So later we will study the denominator term as beta. So finally 5 by 2 means we will write cos square pi y by beta. So this is an important and easiest way to analyze the intensity at any point on the screen. So this is very important for advanced. So now we will analyze the interference pattern, its nature. So interference graph we are going to discuss. Just now we have seen the intensity expression as some I equivalent to 4 I naught into cos square pi by 2. So that equivalent to 4 I naught into cos square theta equal to 1 plus cos 2 theta. So 1 plus cos theta by 2. 1 plus cos theta means pi, 1 plus cos pi by 2. So that equal to 2 I naught into 1 plus cos. So that means whenever we are interested to analyze this graph, so obviously it is going to be a cos function. So whenever it is going to be a cos function, on the screen we are observing interference. This is the screen. So obviously this is going to be a cos function. Suppose in the ydse experiment we are taking, suppose if we are taking this as the central maximum, this is the central maximum. So we will take this as the n equivalent to 1 first bright fringe. First bright fringe. And here also we are having n equivalent to 1, that is first bright fringe. So that means on the either sides we have bright fringes. And these are called as, and this is called as central maximum is it is known to as n equivalent to 0. And this is n equivalent to 1. This is first dark fringe. First dark fringe. Again, this is n equal to 1 means first dark fringe. First dark fringe. So here we can see that for any fringe we will take. So for any bright fringe or for any dark fringes we will take. So the intensities are similar. అంటే బ్రైట్ ఇక్కడ ఎంత బ్రైట్ గా ఉంటుందో డార్క్ అంత ఈక్వల్ ఇంటెన్సిటీతో డార్క్ గా ఉంటుంది. అప్పుడే కదా రీడిస్ట్రిబ్యూషన్ అనేటువంటిది మనం మాట్లాడుతున్నాం. కాబట్టి ఇక్కడ మనం ఏం చెప్తామంటే ఆల్ బ్రైట్ ఫ్రింజెస్ have equal intensities. And also all dark fringes have equal intensities. So that is the thing we need to understand from this thing. So after this condition, now we will discuss about the dark fringes. So formation of dark fringes we used to do. Or we will call the location of dark fringes as destructive interference. Or we will call the bright fringes as constructive interference. So whenever we say the destructive interference, we will take that the path difference x is equivalent to n minus half into lambda. So that is equivalent to 2n minus 1 into lambda by 2. సో ఇక్కడ మనం ఈజీగా ట్రయల్ అండ్ ఎర్రర్ బేసిస్ మీద ఈజీగా గుర్తుంచుకోవచ్చు. ఒకవేళ n ఈక్వల్ టు 0 తీసుకున్నాం అనుకోండి, మైనస్ లాంబ్డా బై 2 అని వస్తుంది. దానికి మీనింగ్లెస్ ఉండదు, నెగిటివ్ పాత్ డిఫరెన్స్ అంటే ఉండదు. సో వీ హ్యావ్ టు కౌంట్ ఇట్ ఫ్రమ్ n ఈక్వల్ టు 1, n ఈక్వలెంట్ టు 1 2 3 4. సో n ఈక్వల్ టు 1 means first minimum we will take. And if you need the phase difference, phi, or you may call it as delta phi, no issues, 2 pi by lambda into x. So after substituting this, we get 2n minus 1 into phi. So here equal to n equivalent to 1 2 3 4. So simply I am taking for first minimum. So when it is given that first minimum, you have to take n equivalent to 1. So the path difference x is equivalent to, it is lambda by 2, and phase difference equivalent to phi. So similarly we will do for number of minimums. And we know the expression for the fringe width beta. So that is equivalent to lambda capital D by small d. And we know that the fringe width of bright fringe is same as that of dark fringe. Fringe width of bright fringe same as that of dark fringe. Same as that of dark fringe. So after taking this, so now we will analyze the questions based on ydse. So the first one is beta is proportional to lambda. They will discuss that if the wavelength of light source has been changed from red to violet, so then what happened to the phase width? So whether it is increases or decreases, they may ask. So whenever we used to replace the red by violet, so we know that lambda red is more than lambda violet. So obviously beta red is more than beta violet. Beta violet. So next, after taking beta is proportional to lambda. So we used to think of medium. So B is proportional to lambda, and from ray of x we know that it is 1 by mu. So when ydse shifted from one medium to another medium, when the ydse shifted from one medium to another medium. So then simply we will say beta medium by beta air. Suppose if we are moving the ydse from air to water, let us say. So for such examples, we are taking mu air by mu that particular medium. So we will use. And also, in the similar case, we are taking about angular fringe width. So first we focus on angular fringe width. So angular fringe width means it is the angle made by any particular fringe at the source. So that is beta by d. That is beta by d, or we will call it as theta. So beta by d. So this is beta by d is nothing but lambda by small d. Lambda by small d. Beta by capital D is equivalent to theta. Theta equivalent to lambda by small d. So here lambda we used to call it as the wavelength. Small d, it is nothing but distance between two slits. Distance between two slits. So from here also we will take theta is proportional to lambda, lambda is proportional to 1 by mu. So therefore theta medium by theta air equivalent to, we used to take mu air by mu medium. Mu air by mu medium we are taking. So this is very famous. In the previous questions, we have major applications on the upcoming field. In certain field of view, on the screen. So in certain field of view on the screen means the particular distance y is constant. Suppose I'm taking this is the screen. So this is the screen. In certain field of view, so that means this is constant, y is constant. In certain field of view on the screen, if n1 fringes, if n1 fringes are formed, n1 fringes are formed when light of wavelength lambda 1 is used. Light of wavelength lambda 1 is used. And n2 fringes are formed. N2 fringes are formed when lambda 2 is used. So then they need a relation between lambda 1 and lambda 2. So we know that in ydse the most popular relation is y by capital D is equal to x by d. Y is constant. As we are using same device, same ydse, so therefore the distance between slit and screen is same, and the distance between the double slits also same. So what is our final condition is x is equivalent to constant. So we will get n lambda for the bright fringe, n1 lambda 1 equal to n2 lambda 2. Or sometimes we may use n1 beta 1 equivalent to n2 beta 1 into beta. If we have similar condition for the dark fringes, so then also we will get this kind of condition, n1 lambda 1 equal to n2 lambda 2. So clearly we are saying fringes. Fringes means for both bright fringes and as well as dark fringes, the same condition is applicable. So next we are focusing on. So this is very important. The position of nth bright fringe. The position of nth bright fringe from central maximum. From central maximum on the screen. From central maximum on the screen. For example, I'm taking the screen. I'm taking the screen. From the screen, you are observing a position point P. So this is y. So again, we will use the same principle. Y by d is equivalent to x by d. So because this is referring the nth fringe, we are taking instead of y, we will take yn. Yn equivalent to x means n lambda d by small d. So similarly, the position of nth dark fringe. Similarly, we take the position of nth dark fringe as yn dark fringe we are taking. The path difference changes as n minus half into lambda d by small. So in this way we will understand the position of bright and dark fringes. Next, we have a discussion that if we use white light, then central maximum due to all colors are overlap with each other in that case the central maximum is white. అంటే మనం ఏమనుకున్నామంటే normally we use a monochromatic light source, that is maybe sodium vapor lamp mostly we will use. So instead of taking that yellow light, if we use a tube light, so in that particular situation, so what is the nature of ydse? So we will see that the central maximum is white. So adjacent to this we have red color. And at the end we are having blue color. So this is the general discussion. So next we will discuss the maximum possible brightness. అంటే క్వశ్చన్స్ ఎట్లా ఫ్రేమ్ చేస్తారంటే if in ydse if d is equivalent to 3 lambda, then find maximum possible maximum number of possible brightness. So దీనికి ఎలా రాస్తామంటే we know that the path difference is equivalent to d sin theta, that equivalent to n lambda, or sin theta is equivalent to n lambda by t. As given, we know that sin theta is always less than or equivalent to 1, n lambda by d is less than or equivalent to 1. So n is less than or equivalent to d by lambda. So this is very, very important relation. And we know that d equivalent in this present problem we are thinking d equivalent to 3 lambda. So therefore n is less than or equivalent to 3 lambda by lambda. So n is equivalent to. So here we can see that therefore we have 2n plus 1, 2n plus 1 possible maximums. So we have 2n plus 1 possible maximums. So why? Because we have central maximum. So in this way we have n right fingers, and in the downside also we have n right fingers, and the central maximum also right. So that's why we will take 2n plus 1 possibilities. So in the present problem, therefore, the possible values are 2n plus 1, that is 2 into 3 plus 1, 6 plus 1 equivalent to 7. So in that way we used to think. And in ydse or a superposition we call, so we have a very famous question. So that is the ratio between maximum intensity to minimum intensity. This is very, very important. I maximum by I minimum equal to simply we take root over I1 plus root over I2 by root over I1 minus root over I2. Are that equivalent to A1 plus A2 by A1 minus A2 A1 minus A2 first. Or else we are having another form, that is root of W1 plus W2 root W2 by root of W1 minus root of W2 whole square. So here W is nothing but slip rate. So W is nothing but slip rate. And so we are deriving everything on the basis of this I is proportional to amplitude square. And we know that A maximum is equivalent to A1 plus A2 and A minimum equivalent to A1 minus A2. So this is very, very important. You can come across a bunch of questions on the basis of this topic. So ఇది నాకు చాలా important. So next afterwards I am taking fringe visibility V. So that equivalent to I maximum minus, this is a formula, I maximum minus I minimum by I maximum plus I minimum. If it is given that the ratio between the intensities I1 by I2 equivalent to n, let us. So then by substituting here we will get 2 into root of I1 I2 by I1 plus I2. 2 into root of I1 I2 by I1 plus I2. Or we will have 2 into root of n by 1 plus
1 plus
1 plus 1. So this is very important. Fringe visibility V is maximum when I minimum equal to 0. So that means V should be maximum when the negative value is equivalent to 0. So simply we are taking, therefore V is equivalent to 1. And we have poor visibility. We have poor visibility when we have I maximum is equivalent to I minimum. So in that case, visibility equivalent to 0. Yeah. And the two more things we are left with. If the slit widths are unequal, so that means, so W1 is not equal to W2 we are taking, and I1 is not equal to I0. Then minima then minima is not equal to 0, then minima will not be complete dark. The minima complete. Next, we are taking one more thing. So that is missing wavelengths. This is very important. Missing wavelength in front of one slit. In front of one slit in YDS. In front of one slit in YDS. So actually, we have been taking that this is a double slit. So this is a screen we are taking. So in front of one slit means we are taking like this. So we know that this is the center, and we know very well this distance is D. This distance is D. So from the central maximum, this is the central maximum. So this is Y. So from the diagram, it is very clear that Y equal to D by 2. Y equal to D. So here we will say that against the screen. So missing wavelengths. Missing wavelengths means bright fringes are absent. So simply we will understand that this is the condition for destructive interference. అంటే బ్రైట్ ఫ్రింజెస్ లేవు అంటే డార్క్ ఫ్రింజెస్ ఉన్నాయి అని అర్థం. Again for this also we will use the same logic. Y by D is equivalent to X by D. Y by D is equivalent to X by D. Y means it is clear from the diagram D by 2 by capital D. X means we are getting dark fringes. So therefore I am taking the path difference conditions as N1 is equal to lambda by small d. Or we get lambda equivalent to D square by 2n minus 1 into capital D. So the possible missing wavelengths are we get by substituting n equivalent to 1 to 3. So that is lambda equivalent to D square by capital D, lambda equal to D square by capital D, and D square by 3D, and D square by 5D. 5D and so on. We will get this. So after this, so we think of lateral displacement. Lateral displacement of fringes. Suppose in one of the path, if a thin mica sheet like material is introduced, so then the entire fringe pattern is shifted by some n fringes. So this is S1 we are taking, and this is S2. This is S2 and this is S1. So if the entire fringe pattern shifted by n bright fringes, So by substituting y equal to n beta, we will get our desired condition is for path difference. X is equivalent to mu minus 1 into t. Suppose if we use instead of taking single mica sheet, so we will take 2 mica sheets. So we will consider 2 mica sheets. So this is mu1 and this is refractive index of mu2 of equal thickness. So here in this case the path difference is equal to mu2 negation mu1 into t. mu2 negation mu1 into t. Okay. And after this, this is important for your exams. Multiple slit interference pattern. So we have a number of slits, and each slit is making an angle pi with respect to other. So the light is emitted at those slits. So all these are slits. All these are slits. So we will get they will ask for the resultant amplitude of light which is emitted from these slits. So we have an expression AR equal to A naught into A naught is the amplitude from each slit. A naught is the amplitude of light from each slit. A naught into sine n phi by 2 by sine phi by 2. Similarly, we will get the resultant intensity I naught into sine n phi by 2 by sine phi by 2 sine phi by 2 sine phi by 2 whole square. So all this is about ydse. So in another session we think of the diffraction and as well as